We also have, as space observatories, allow us to really resolve things beyond Earth's atmosphere with very high precision, that have allowed us to fundamentally do some of the things that we know or we thought we knew after its launch in the 90s. Of course, the problem with this is all of these are basically tied to things through electromagnetic radiation. And if I go back to the original picture that I showed, right, we break down what is actually present in our galaxy in terms of a census, right? If we break down the matter in the universe, 85% of it is dark matter, right? It is essentially something we know has to be there. We can infer its existence from the presence of gravitational, from how it holds galaxies together, but we've never been able to see it. And as far as we know, it does not interact with luminous matter or with the electromagnetic field. Of the things that actually do make up the universe, only 15% is regular matter. And of that 15%, only 6% is in the stars that we typically see in telescopes. Even of those 6%, 20 of them are already dead. And so I'm going to focus on this last bullet point for a large part of the talk today. If 20% of the stars out there are already dead, how can we actually observe them if they're not generating large amounts of electromagnetic radiation? And so I'm going to talk today about how we can observe a lot of these objects through gravity itself. And to do that, I'm going to take a little bit of a step back and sort of review how we understand gravity today. So the classic picture of gravity that was learned in school and that is actually still used for 99% of even astrophysical calculations or space-based calculations is based on Isaac Newton's theory of gravity. Now, in Isaac Newton's theory, gravity is an invisible force that permeates the cosmos. You probably remember it from school as some force that is parameterized by minus g, the gravitational constant, times the two masses, divided by the distance between the two masses. And even though Isaac Newton couldn't exactly explain what was driving this force, he realized that this inverse square law described very well how the motion of planets, stars, and things on Earth. And so essentially you have this visible force that is keeping things in orbit. Now, sort of a central underlying assumption of Isaac Newton's theory, you essentially have this dynamics playing out on some sort of stage, right? And we call that stage space and time, right? In Isaac Newton's theory, the masses are allowed to move, but space and time are fixed. They are essentially the fixed background with which we measure distances and measure time on clocks. In order to talk about how we can use gravity to measure some of these more exotic objects in the universe, like dead stars, I need to talk a little bit about how we moved beyond Isaac Newton's gravity. And so the next step beyond Newton's gravity is, of course, Einstein's theory of gravity. And in Einstein's theory, he essentially does away with both the invisible force connecting these objects and the rigidity of space and time itself. So in Einstein's theory, space and time are unified into a single object that we call space-time and allowed to deform in the presence of mass. And so in Einstein's theory, space and time are allowed to curve. I usually describe this to people as, imagine you have a trampoline and you throw a bowling ball into the middle of the trampoline. It's going to curve the fabric of the bowling ball towards it, right? And if I try to roll a smaller object, like a ping pong ball or a tennis ball, along the surface of the trampoline, it's going to curve in the same direction as the bowling ball because that's the closest you can get to a straight line, right? It wants to naturally get a straight line, just like the thing that I roll, but the closest it can get, as long as it's stuck to the fabric of the trampoline, is deflecting towards the bowling ball. And it turns out Einstein's theory works largely the same way. The person who sort of summed it up best was the physicist John Wheeler, who basically said that space tells matter how to move and matter tells space how to curve. So if I have some mass in space-time, it's going to deflect space-time towards it. It's going to curve space-time towards it. And then in that curved space-time, the closest I can get to an actual straight line curves in the same direction as that mass. But there's some additional interesting implications of allowing space to be not completely. And to understand this, we can go back to the analogy from the trampoline. So if you're sitting at the edge of the trampoline, and I have two bowling balls that are orbiting around each other, that are moving around each other in the trampoline, you could feel the vibrations of the trampoline at the edge, right? It turns out that in Einstein's theory of gravity, we essentially encounter the same effect. So in Einstein's theory, it turns out that if you have two masses that are orbiting around one another, you develop these waves, these essentially almost standing waves in space-time that are allowed to travel outwards. Now, for those of you that are very familiar with electromagnetic theory, these are actually transverse waves in space-time traveling outwards from the source. The same way that if I have an electric field and I jiggle a charge back and forth, I get an electromagnetic wave moving one direction. In gravity, if I have two masses, they deform space-time in such a way that I actually get waves traveling outwards from the source. These waves are what we call gravitational waves, or literally ripples in space-time itself. Now, in the electromagnetic case, right, what you do is you jiggle a little charge, and then an electromagnetic wave starts moving in one direction. In this case, right, in the case of gravity, the thing to keep in mind is that what gravity fundamentally is, what space-time fundamentally is the way we measure the distances between objects. So if a gravitational wave is passing into the screen here, let's say I have just a grid of masses out in the screen. What's going to happen is that if the wave passes into the screen, it's going to cause the measured distance between those objects to fluctuate very slightly. And so as the wave passes through the screen, it actually creates these breathing motions in the position of objects as I measure them. Now, fundamentally, if I want to measure a change in distance, what I do is I get a ruler, right? And so what people have done is essentially build an ultra-precise ruler. And that's what the experiment that I'm showing now on the screen essentially is. So what I'm showing you are 3 sites of the Laser Interferometer Gravitational-wave Observatory, or LIGO. And what LIGO fundamentally is an ultra-precise ruler. It is probably the most precise distance measurement. It is the most precise distance measurement that humanity has ever done. And it's achieved using something called laser interferometry. So the idea is that I take a laser beam, here represented as sort of the hubs of these 3 gravitational wave detectors, and I'm going to split the laser beam in half. I'm going to shoot it down these 4-kilometer long tubes that are at a 90-degree angle to one another. And what happens is, after it travels 4 kilometers, it's going to hit a mirror at the edge of each of these arms and get reflected back to the center. When that happens, I'm going to recombine the laser, right, in such a way that normally, if there's no gravitational wave passing through, I get what is called complete destructive interference. I've tuned the thing in such a way such that essentially the peaks and troughs of my laser light, I just zoom this ahead here, are going to cancel out when there's no gravitational wave. But then, as a gravitational wave travels through the LIGO site, it's going to change the distance along one of these arms, and it's going to, and it's going to essentially create light at the edge of my photodetector. So whereas before the 2 arms were completely canceling out the light, when a gravitational wave passes through, it changes the distance along those arms very slightly. And instead of complete destructive interference, I get constructive interference here. And so what I measure, just from a photodiode right here, is essentially peaks in the light itself that are allowed to escape from this. So the fundamental idea is that as the wave travels through, it changes the shape of LIGO, and that allows me to measure the change in distance from gravitational waves. To give you a sense of exactly how small these changes are, the difference between a standard baseline LIGO, a fully extended LIGO from a gravitational wave, 10 to the minus 18 meters. To give you a sense of exactly how small that is, 1 meter is roughly speaking the size of us, give or take. If I divide that by 10,000, that gives me 2.1 meters. which is roughly the width of a human hair. If I divide that by 100, that gives me to 10 to the minus 6 meters, which is roughly the wavelength of light. If I divide that by another 10,000, that gets me to roughly the atomic diameter, so where the electrons are orbiting around nuclei. If I divide that by 100,000, that gets me to the nuclear diameter, roughly the size of a proton or a neutron. And if I divide that by another factor of 1,000, that gets me to 10 to the minus 18 meters. That is the sensitivity of a gravitational wave detector. We're talking about something that is measuring 1,000th of the diameter of a proton, which is an absolutely absurd measurement to be able to do. What's even more absurd is that it appears to have worked. So what I'm going to play now is the first gravitational wave event. I don't know if you're going to be able to hear this, but you will be able to see it. And what you're looking at is this what's called a spectrogram. And I'm essentially showing the frequency of the wave that is detected in the LIGO Livingston site in Louisiana and the LIGO Hanford site in Washington as a function of time. The wave itself appears in the last 0.2 seconds of this. And so you'll see it's going to play 4 times. The first 2 times it's going to be the raw output just plugged into speakers. The second 2 times I'm going to lift it up frequency by about 400 hertz. You can hear it very well. And so as I play this, I'm just going to point my speaker straight towards the microphone. What you see is that there's this pulse. And so that pulse represents the first detection of gravitational waves in 2015. And this pulse, you can see here that the wave itself is increasing in frequency. The peaks are getting closer together, and it's increasing in amplitude. It's getting louder as time goes on. This wave comes from the deformations in space-time caused by the merger of 2 black holes, roughly 1 billion light years from Earth. These black holes are about 30 and 35 times the mass of our sun. About 1 billion years ago, they spiraled into one another, emitting gravitational waves as they go. These black holes are massive enough and they're moving fast enough that they can deform space-time. The gravitational waves carry energy away from the system. They cause the orbit to decay. Black holes spiral into each other. Until eventually, 30 and 30 solar mass black holes merge, create a 62 solar mass black hole. We can then infer the existence of by fitting the wave to detailed predictions from gravitational wave theorists.
Hey,
and so you might have noticed that I said we have a 30 solar mass black hole. It merges into a 35 solar mass black hole, and we're left with a 62 solar mass black hole. That extra 3 solar masses of material was converted into pure energy. So take E equals mc squared, put in 3 solar masses of material, so that's 3 times the mass of the sun, to pure energy. That energy is purely in gravitational waves, and that's what we see here on Earth. At the time, this was the most energetic event we had ever witnessed as a species. If this amount of energy had been instead emitted as visible light, the single event would have outshone every star in the observable universe by a factor of 50.
And so the question that I want to address is, where do these black holes actually come from? How do you actually get black holes that are 30 times the mass of the sun? We kind of know the answer to this, basically speaking. You start with a massive star, the 60 or even 80 times the mass of its sun, of our sun, it very rapidly, in 7 to 8 million years, will expand to be a giant before eventually being destroyed in a supernova explosion. And we think during these processes, cores of these stars become, if they're massive enough, become black holes. The dead remnant of the star can no longer hold itself up against gravitational collapse because the fusion that was holding the star up is no longer there. And essentially all of that material collapses inwards into a single region of space. And so the reason this was surprising was before that first detection of gravitational waves on September 14th, everything we knew about black holes in the local universe, everything we knew about black holes from stars had come from electromagnetic observations. the majority of it had actually come from X-ray binaries, right? We see a black hole that's wandered too close to a star. It starts accreting matter from the star. This in turn creates a huge disk around the black hole that heats up and emits X-rays. And so all the black holes that we had seen were about 5 to 15 times the mass of the sun. There were a few possible detections more massive than that, around 20 solar masses, but they were a little hard to get the systematics down. And so the reason I have this date here is because September 14th represents the first detection of gravitational waves. And so here I've represented on this plot as two black holes that are 30 and 35 times the mass of the sun merging into a single black hole. This is an event GW 150914. GW for gravitational waves. 150914 is just the date. And since then, we have detected a huge number, nearly 100 of these mergers. We have now detected the majority of black holes that we've detected through gravitational waves, which is pretty wild, right? This has happened only in the past 10 years, give or take. But we still have this fundamental question that we don't know how to answer, which is namely, where did they all actually come from in the first place? Right? It turns out it's pretty easy to form black holes, as far as we know, but it's very hard to get two black holes close enough together because they're so tiny to merge due to gravitational waves. So if I have two black holes that are 30 times the mass of the sun, they have to be less than the Earth-Sun distance in order to merge within the age of the universe. And so when we look at the night sky, right, as I'll probably know, the majority of stars that we see are actually binary stars. And so that's one way you can produce binary black holes. You start off with two massive stars. It turns out actually that the more massive the star, the more likely it is to have a binary companion. And so you start with two stars with two massive stars. They collapse to two black holes. And if you get the mass transfer right, you can get the two black holes close enough that they will merge within the age of the universe. But that's not the only way that we can do this. Another option, we know, of course, that many of the stars we look at are not actually single objects. They're large conglomerations of stars. So I'm going to zoom in now to the Southern Hemisphere globular cluster 47 Tuck, which instead of two stars is a collection of millions of stars. 47 Tuck has about ballpark about 1 million stars in there. And so turns out that if you look carefully at two stars, it's very hard to make some of the largest black holes that LIGO has seen. We can kind of explain things up to 30 solar masses, but since then, LIGO has seen things that are 60, 70, even 80 times the mass of the sun. And it turns out it's very, very difficult to make those with two stars. I'm not going to get into the details tonight. There's a great paper from Lika von Soon about 3 years ago that goes into this. But I fundamentally am a dynamicist. I'm interested in how stars move around in space. So if we can't make something with two stars, my natural inclination is to just keep throwing stars until we can explain something. So this is the cluster 47 Tuck. It's a well-known Southern Hemisphere globular cluster. A lot of what my group works on, a lot of what I work on, is simulate these star clusters over time. And so to do that, I'm going to talk just briefly about how we actually model these star clusters themselves. So let's take a slightly idealized picture of a star cluster. Okay. So if I give you a collection of stars, and I want to know what is the gravitational force between one star and every other star, we know how to do this, right? We go back to high school physics, an arrow between the two, just in Newtonian dynamics, and we can calculate the force between two objects, just again as the sum of as the product of the two masses divided by the radius squared. Don't worry about what the i's and j's are. And so if I want to calculate the force, all I have to do is take the force from every star and add it to the force of every other star. But there's a few problems when we try to do this. First of all, there's a wide range of timescales involved in these simulations. So the time it takes a star to orbit around the outside of the cluster is about 100 million years for the largest clusters. But we can form binary stars. So that's two stars that are orbiting on each other inside the star cluster and orbit around each other every 100 hours, right? So that makes it for a problem. The second problem is that this problem scales as the number of stars squared. Because every time I want to know the full force on a star, which is going to tell me where that star is going to move 10, 20, or 100 million years from now, every time I add a new star, I have to calculate not only the new force from that star on my current star, but I have to calculate the future trajectory of that star with respect to every other star as well. And so as I dial up the number of stars that I want to consider, which is what we call n, the number of stars, that problem scales as n squared. And so the gravitational in-body problem, as it's called, has a long and storied history in both analytic math and even computation. So the first in-body simulations that I know took place about years ago. Now, some of you that have worked in computers might realize that we didn't actually have computers in 1941. So what exactly is going on here? So this paper from Holmberg shows an idealized galaxy comprised of about 37 stars. And so what they did, because they didn't have computers at the time, is they wanted to know what caused the spiral arms in galaxies that we see. And so they wanted to simulate one of these galaxies forward in time. And so what they did was they created a bunch of stars on little trays using light bulbs. Each one of their stars is actually a tiny little tray with wheels on it. It's got a light bulb with a well-known luminosity. It has a photodiode that tells you how strong the light is from every other star. And so you can approximate gravity and strip the light from all of the other light bulbs. And so you do that, you get a large number of graduate students, don't want to get drafted into World War II, and you have them move their little light bulbs across the gymnasium floor of Cambridge over several years. And so, mind-bogglingly, one of the simulations they did is they tried to throw two of these galaxies at one another. And then, after many, many months of moving these light bulbs, they actually showed that the interaction between these two galaxies was enough to create the spiral arms that we see. These are what we call tidal effect, essentially the tides from one galaxy on the other. Since then, with the advent of computers, things have improved a little bit. The first computer simulation I know about, at least the first one with art, comes from Olaf Lindblad in 1961. And he's looking at the development of bars in galaxies. So he's doing this on, I also just love this particular video, the first visualizations I know of. Doing it on a best computer, you can see how they represent the time up here, a little clock. And for many, many cycles, because they have differentially rotating stars, you actually see the galaxies start to develop not only arms, but a bar-type instability. So this is one of the ways we think that you actually form bars in galaxies. Fortunately, things have improved a little bit since then. And roughly speaking, you can create this plot of how many particles are you able to consider as a function of year. So going back to the 60s, we were only doing computer simulations of 10, 20 particles. Things have improved then, up to hundreds, thousands, even tens of thousands. State of the art for the gravitational in-body problem was roughly developed, is currently about 1 million particles. It's developed by Long Wang, who was a graduate student at the time. Now he's a professor. And he was able to do large-scale simulations of globular star clusters. The nice thing about these simulations, they called the Dragon simulation, are that you're not just limited to looking at the stars. So in this plot on the left, the central circle represents all this, what you would actually try to observe this cluster. But it's a simulation, break it down into all the constituent parts. You have sequence stars in the top left, giants in the top right. You can break it down into binary stars, asymptotic giant branch stars, dwarfs. You can even identify the black holes, which are shown on the right, which you would never be able to see through any telescope. The problem is, this still took about 13 months of computer wall time, right? So even though they had a massively parallel GPU computer to run this on, it still took more than a year to actually simulate one of these star clusters over its entire life. So the other thing you can do is you can come up with ways, if you go back to the drawing board, you come up with ways to try and optimize this problem. And there's a couple of different ways you can do that. One, you could try to come up with new computers, what we call hardware optimization. So in the 90s, there was an entire industry developed to create what are called gravity pipes, or grapes. They were essentially special purpose hardware developed by Jun Makino, you can see in the picture here, designed to do one thing and one thing only, and that is sum together the forces of stars on other stars. Now, what you're doing there is you're essentially developing a large-scale summation over huge numbers of positions. These gravity pipes used to run for anywhere from $50,000 to $200,000 a pop in late 90s money. As those of y'all that are familiar with computers, these were essentially made obsolete by the first commercial GPUs. Because once a GPU came out, it's doing essentially the exact same type of calculations for a fraction of the cost. So we can use specialized hardware, or GPUs. We can also come up with different algorithmic enhancements, different ways to sort of tweak the physics. Or we can use some of what we know about the actual star clusters themselves to simplify the problem. And this is some of what my group does. We assume star clusters like this are mostly spherical. We assume that they evolve fairly slowly compared to how quickly the stars are orbiting around them. And in doing so, we can actually reproduce the time evolution of these clusters over many, many billions of years. So I'm showing here a plot, pretty much the only, I think, scientific plot I'm going to show in this talk, that shows what we call the Lagrange radii of this cluster over time. The red lines represent our method. The black lines represent the in-body method on wall. And what you can see is that most of the lines essentially agree. These lines represent the radius from the cluster center close some fraction of the cluster mass. So the core radius, the half-mass radius, basically all of the mass in the cluster is where it should be based on rapid simulations. The advantage to doing this is that while the in-body simulation took 15 months, our simulations take about 2 months. And so that's sort of the name of the game of what a lot of what my group is doing. We're essentially trying to go back to well-known star clusters, like 47 Puck here, and simulate them on the computer. On the right, I'm showing a synthetic observation of a young star cluster as viewed by JWST. Right? This is a movie by an undergraduate that was working with me back at Carnegie Mellon. And the nice thing about these simulations is that we can play forward the clock and ask, what are these star clusters going to look like billions of years in the future? The other nice thing about this, like I said, is that by trying to simulate as best we can realistic star clusters, we can zoom into the central regions and really see what's going on with the black holes in the center that we couldn't identify otherwise. So what I'm showing now is a simulation from my PhD thesis. And what this shows is 5 of those stars in the middle surrounding a star cluster. And if you look at the center, you see this sort of swirling Matisse-like painting. That's actually 50 black holes that have sunk into the center of this star cluster and are undergoing several different interactions, gravitational interactions. The long-term evolution of these systems is such that the black holes will migrate into the center of the cluster. Once they essentially form this almost black hole nucleus, this compact region in the center of the cluster, where the density of black holes can be several hundreds or thousands or even tens of thousands of black holes per parsec cubed. And these high densities allow not only 2-body encounters, gravitational encounters, but even 3-body encounters between black holes. And so over time, what this looks like is that as I drive the simulation forward, eventually you're going to see that it starts forming binary black holes. This theoretical work has allowed us to make several key predictions about gravitational waves. It allowed us to correctly predict the masses of the first gravitational wave detection. We also were able to show that black holes can merge in clusters, create a massive black hole, and then find another black hole and merge again. And if you look at the movie here just now, eventually we form, in this simulation, single binary black hole that may or may not merge many billions of years later in the cluster. And so the question is, we've shown theoretically that you can produce these systems. How do you actually know that what light is seeing are coming from these star clusters? Well, to answer that, we need to go back and look a little bit at what happens once I form one of these binaries. Once I form a binary, I'm not done yet. I'm going to continue to hit that binary with other stars and other black holes in the cluster. For some reason, this movie, even though it's more simple than the other ones, doesn't work quite as well. And so what happens is, after I've formed a binary, I continue to bombard it with other black holes and stars, creating these chaotic encounters that allow me to shrink the binary's orbit until eventually gravitational waves can take over. Now, the nice thing about these encounters is that they essentially scramble everything about the original binary, right? The masses stay the same, but the orbit itself and the spins in particular of the binary get completely scrambled during the encounters. And so what we want to know, can we use this scrambling as a way to understand where the black holes that LIGO sees are coming from? And so the question I want to answer is, how do we tell that something is coming from a dynamical environment? And so one way we can do this is by using spins of the black holes. It turns out that black holes spin essentially the same way that planets spin. So ignore some details of the plot on the right. But the picture to have in your mind is the same way that the Earth is rotating, is spinning on its axis, while it is orbiting around the sun. Black holes can spin on their own axis while they are orbiting around each other and emit gravitational waves. And it turns out that spin actually can imprint itself onto the gravitational wave itself. So what I'm showing right here, two black holes that are spinning in the counterclockwise direction. The arrow indicates that they are spinning in the counterclockwise direction. And they're orbiting around each other in a counterclockwise direction as well. That's what the red arrow indicates. And what I'm going to do is I'm going to rotate the spin axis of black holes down by 90 degrees. And on the right, I'm going to show you what that does to the gravitational wave over time. So essentially, this would be like, the Earth is rotating in basically the same direction as the sun. Their spins are aligned with each other. I'm now going to ask what would happen if I had taken one of those spins and misaligned it by 90 degrees. And so as I rotate the axis, the gravitational wave on the right develops these beats, right? And so what happens is that it turns out when the spins are misaligned, the entire binary wants to proceed around the total angular momentum of the system. What that means in these terms is the same way that you spin a top and it starts to wobble back and forth due to rotation. It turns out that by misaligning the spins, the entire binary is going to start to rotate in 3D space. So the entire binary starts just rotating like a top. Now, LIGO is more sensitive to gravitational waves when you're looking top down on the binary than when you're looking at the edge of it. So it's stronger now than it is now. What that looks like in the gravitational wave detector are essentially beat modulations. It would be like if you grabbed the volume and started turning it up and down at random intervals. That's what these here represent. So furthermore, if I continue to rotate the spins until they are now anti-aligned with the orbit, I still get this huge, the beat modulations are gone, but I still get this huge shift in the frequency. Right? And so it turns out black holes from stars, from binary stars, they live together, they die together, the same way that the Earth and the sun are spinning in roughly the same direction. It turns out that stars that are that close to one another also spin in the same direction. And so for isolated binaries, we expect the black holes to have spins that are roughly pointed in the same direction. But dynamical processes are chaotic. Right? Three-body problem is fundamentally chaotic. It totally scrambles everything. I'm a black hole binary encounter a star black hole. And so we expect the spins to be completely random. And so half the time, we expect the spins to be anti-aligned, at least a little bit, with with their orbit, and half the time we expect them to be aligned, right? Because if I pick where this angle where is one angle with respect to another, I basically expect them to be negative half the time and positive half the time. And it turns out, if I go back and look in the LIGO data and ask how much of the systems appear to be negative, it turns out to be about 27%. Now, from clusters, it's completely random. So I expect basically half the time the spins to be negative, half the time the spins to be positive. So if I multiply this by 2, this leads us to the conclusion that anywhere from 25 to 90% of LIGO's binaries may be formed in the cores of these star clusters. All right, so that's what I wanted to talk about with LIGO. If we have maybe another 10 minutes, I'd love to talk about the origin of gold and neutron star mergers, but that's really up to y'all.
I'd love to hear it.
Okay. So I have a slightly provocative title here, but to go back to the plot that we had here. So I'm showing right now only black holes, but it turns out one of two things can happen when a star dies. The other option, the other evolutionary pathway, if it's massive enough, is that you form neutron stars, and that's things that are typically 1 to 2 solar masses. I cut off this plot a little bit, and so to go back to this exactly, the main cutoff basically has to do with the mass of the star. If I start off with a massive star that's 20 times the mass of the sun, I have a movie that I showed you earlier, right, where I have essentially a massive star evolves over about 10 million years, eventually evolves to be a giant, and then a supernova explosion occurs, and I'm left behind with a black hole. On the other hand, if I look at something that's less massive, so if I look at something that's about 10 times the mass of the sun, I still get a supernova explosion. Oops. Let me redo that. I still get a supernova explosion. But what I'm left with is not necessarily a black hole, because it turns out the core of the star after the supernova is not dense enough to collapse to a black hole. Instead, what I'm left with is what we call a neutron star. This object that you can see right here. Neutron stars are unbelievably dense. They're not dense enough to form black holes, but they are still probably the most dense objects that we know of in the universe. To give you some perspective, the black hole, the neutron star that I'm visualizing here, is roughly the same size as Brooklyn, but it's about 1.5 times the mass of the sun. So take 1.5 suns, crunch it down to a space roughly the size of Brooklyn or the Bronx, and you have a neutron star. And so what I'm going to play now is the output of LIGO on August 17th, 2017. On the bottom, you see that same gravitational wave spectrogram that I showed earlier. On the top, you're going to see counts per second from the Fermi Gamma Ray Telescope. And so over time, you see this increase in frequency and amplitude as the neutrons spiral towards each other. Then 2 seconds later, we see a large peak in the gamma rays themselves. That's because the key difference between neutron stars and black holes is that neutron stars, when they merge, emit light. They emit photons. And so once the gravitational waves were detected, everybody knew that this was going to be a massive source that everyone wanted to observe using classical telescopes. And so what I'm showing here are the text messages between Dave Coulter, who is a graduate student at UC Santa Cruz, and his PhD supervisor, Ryan Foley. And if you read through it, it starts off with Dave basically telling his advisor to stop what he's doing is check his email. His advisor, Ryan Foley, is in Copenhagen, taking his kid to an amusement park. And his grad student, I think this is midnight, roughly their time, is basically trying to get his advisor back to actually go look at this object. And initially, if you look at the bottom of this, if Ryan thinks that his grad student is basically playing a joke on him. But eventually he's like, all right, let's actually do this. So they fire up the Las Campañas Observatory, excuse me. If you look at the end of the text message joke I got there, Dave is basically screaming at his advisor that he is not joking to actually get on and fire up the telescope. Eventually they do. And so what has gone out from LIGO at this point is an alert that there's something potentially interesting to observe. And so if we look, however, at what LIGO has actually detected, LIGO is not the best precision instrument in the world. So we're looking at the night sky right now. What I'm showing right now is the initial uncertainties provided by the Fermi Gamma Ray Telescope. They only detected through their alert measurement systems. But if I add to that the uncertainties provided by gravitational waves, by LIGO, suddenly there's an overlap between the gamma rays and the gravitational waves. If I add in Vera, which is an Italian gravitational wave detector, suddenly we have a small, relatively speaking, region of where this could have come from. And in fact, if you look at the distance that it was thought to have occurred at, there's only about 50 or so galaxies that could host binary neutron star mergers in that volume of space. So at this point, Ryan Foley's group is now on Slack, searching through their new images that they're taking and comparing them to reference images. And so Charlie Kilpatrick, who was a postdoc at the time, found something and sends it to the Slack. So on the left, you're looking at the screenshot of the reference image. And on the right, you're looking at the same image taken by them, at the Las Campañas Observatory. The main galaxy is circled in green. If you look at the image on the right, there's suddenly a new star about a centimeter to the top left above the galaxy that is not there in the reference image. So this galaxy, NGC 4993, Foley sends out an entire astronomical community, and everybody swivels their telescopes to look at this galaxy, NGC 4993. I'm going to zoom into it right now. As we clear up the image a little bit, you can see the galaxy with the new image, with the new star right here. Now, this essentially set off a massive race looking for more of these objects. And so what I'm showing on the top are the initial observations from LIGO and Fermi, the gamma ray telescope. What I'm showing now are all of the observations of this object that occurred over the next essentially 2 months. Each tick mark here represents a distinct observation from different telescopes across different bands. So I've got gamma ray observations, UV and X-ray observations, optical observations. You can see every telescope that measured this optically is listed under there, same for infrared and radio. This paper, written on the first double neutron star merger, called Multi-Messenger Observations of a Binary Neutron Star Major, was an absolutely massive ordeal. And it actually, if I take apart the author list, it takes about 10 pages. So this is the single author list for this paper. Sorry, 11 pages. This paper single-handedly can take over 3,000 astronomers, which, depending on how you count, is roughly 1/5 of all professional astronomers. So this was by far the most exciting astronomical event probably of the last decade. But to return to my question, how do we actually get gold out of this? So the answer comes from neutron stars themselves. Like I said, that neutron star material is extremely dense. Other than black holes, these are the densest objects we know. And I mean, we're talking densities of roughly 10 to the 17 kilograms per meters cubed. So I usually give this part of the talk at Astronomy on Tap events. So I usually reference it back to drinking in some way. And so in that sense, if I had 2 pint glasses worth of neutron star material, that would be roughly 10 to the 11 tons, which is roughly the same mass as Mount Everest. And so I have what are essentially these 2 atomic nuclei in space. They're extremely dense. They're almost pure neutrons. The density is actually so high that it has forced the protons and electrons back into each other in an inverse decay procedure and produced more neutrons. And so what happens is I'm about to collide at relativistic speeds 2 neutrons to each other, 2 giant atomic nuclei into one another. When I do this, what's going to happen is that these two nuclei collide, and it essentially acts as a giant particle accelerator in space. So I merge two neutron stars, emits a huge gamma ray burst, and then as the light here goes from blue to red, what powers the blue, the initial blue, was outflows. Red is actually powered by radioactive decay. And so what's decaying? Well, it turns out it's the high atomic elements that I'm creating during the merger of all these neutrons. If I take a look at the periodic table, we know, roughly speaking, where most of the elements on here come from, but they're not always from where you would expect. So the Big Bang produced essentially only hydrogen and helium. It's a tiny bit of lithium, but not much. Everything else on the periodic table was forged in stars. And so everything from roughly lithium, number 3, all the way up to iron at 26, we know how to create in the cores of massive stars. Nuclear fusion in stars can produce everything roughly up to iron. But everything with an atomic number greater than 26 turns out to be pretty difficult to stars, because it turns out once I start adding neutrons and doing nuclear fusion beyond iron, it's very difficult to move up too high with the thing radioactively decaying back to iron or more frequently nickel very, very quickly. The only way to do this is if I can dump a large amount of neutrons onto a material very, very quickly, which is exactly what happens when two neutron stars merge. So I think most of us have probably seen the periodic table at some point. Most of us have probably, many of you have probably seen what I'm showing now, which is an element of the guides. So this is essentially a more complicated version of the periodic table. The Z, which is pointing upwards, shows the same atomic numbers as before. You've got iron at 26 down here, hydrogen, helium here, all of the really fun stuff, plutonium, or uranium, americium, are all up here. The bottom is showing the number of neutrons that it has. So what element it is determined by the number of protons. But I can have isotopes of those elements, each of which have the same number of protons, but wildly different numbers of neutrons. And so what I'm going to show here are the abundances of elements that are created during a neutron star merger. I start off with a large number of things just north of iron, all right, 26, give or take, 28. That's going up to nickel. And then suddenly, when these things merge, this shoots upwards. I get a huge number of very high atomic number, very neutron-rich elements. Now, these are highly unstable. They very rapidly decay back down until they eventually can decay to something that's semi-stable. And what those semi-stable things are the islands of stability that form most of the things we know on the periodic table. And so what astronomers often show is not the normal periodic table. We often look at a periodic table broken down according to the origin of the elements. I'm showing now where most of the elements come from. Most of, as I said, hydrogen and helium comes from Big Bang and blue. Most of everything up to, depending on how you count, either nickel, you can get a handful of things, and around germanium, arsenic, krypton, up to maybe 36 from massive stars. But pretty much everything beyond that comes from dark orange, comes from merging neutron stars. This spot has a little bit of dying low mass stars, but we actually don't think most things are formed that way. And so if you look at gold, for instance, the vast majority of it actually comes from double neutron stars. And so this is something that LIGO and gravitational waves have also allowed us to understand better. Because without alerts from LIGO, it's unlikely we ever would have been able to identify any of these systems. All right. So that takes me to the end of my talk. Thank you so much. And I'm happy to answer any questions you might have.
Thank you so much. That was great. Any questions? You can post them in the chat side. John Birch has got a few questions. John, do you just want to come in and ask whichever questions you want to ask Carl?
Well, Carl, while that's coming along, can I toss one in?
Sure.
so all of these events you've described are extragalactic, if I understand correctly.
Yes.
What are the odds of having one of these, in our galaxy? And is that would that be a bad thing for us? But I mean, certainly, yeah, just take it and run with it. Yeah, please.
Yeah. So the galactic rates for these are very, very tiny. Typically speaking, we expect maybe a binary black hole merger in the galaxy every million years, give or take. So that's probably pretty unlikely. Double neutron star mergers are a little more frequent, probably on the every 100,000 years. So for the most part, I don't think, unless a binary black hole merged extremely close to Earth, I don't think we would any implications from the gravitational wave. Gravitational waves tend to pass through normal matter anyway, so they're not typically absorbed the same way that like photons are. So even if we got incredibly strong gravitational waves passing through Earth, unless we were so close to the black holes that we were beginning to get gravitational effects anyway, I don't think we would get any effects directly from that. Now, if a double neutron star merger occurred, if I go back to the movie I was showing of this right here, right after the double neutron merges, it emits this gamma ray burst, what we call a short gamma ray burst. If that was pointed towards Earth at any appreciable distance, you can see the burst right here, that would be a problem for us. I don't know the exact numbers off the top of my head, but definitely there are reasons where if this happened close to Earth, it would probably end all life on Earth. That being said, the rate of these, the opening angle of these is very, very small, so it would have to be in our galaxy and pointed towards us. And the odds of that happening are essentially infinitesimal.
Yeah, okay. And then the other question I had was, how, I have basic understanding of how the interferometer, LIGO and Virgo work, but how are you able to? Well, I would think that it would give you maybe a two-dimensional vector to the source at best. How do you with something as simple as two axes that are flexing for each other, and you're measuring the aggregate output of those two axes, how do you get a three-dimensional coordinate sphere out of that?
So you actually don't get any position. So you actually don't get any position from a single interferometer. Where's the picture? Because you see the deflection, the differential change along the two arms. You have no notion from that. The only thing you get from that is an amplitude. The only way you can get a sort of sky localization is through time of arrival triangulation. So the sites are the two LIGO sites are, I should remember this, but it's I think on order of they're 3,000 miles apart, and so the speed of light travel time between there is I want to say about 300 nanoseconds. I might be getting the number wrong there. No, that can't be right. There's no way we'd be able to see that. On the order of milliseconds. And so if you see the different times in the different interferometers, you can use that to triangulate the sky. And that's essentially what this does. So if I go back to this movie right here, the reason that worked, the only reason this worked is because I just play this here. They were able to triangulate between the three gravitational wave detectors. So it only had LIGO, which is only two sites. They were able to constrain it somewhat, but they still had two large banana shapes on the sky. Once they added in the third one, time of arrival triangulation is enough for you to actually get a single point of the sky. Now, it doesn't get you a real point because you can only measure so accurately the time of arrival. That does give you at least some region to go look at.
Wonderful. Thank you so much. Paul, I'll hand it back over to you.
Okay, thanks, Chris. We saw. Oh, go ahead.
My name is Manjunath Rao. If you can show your last slide that you showed just a few minutes ago, I have a question about that.
This one?
Yeah. So here we see all these different elements and they have different colors here. So the brown one, the sort of the orange color one is the merging neutron stars. The yellow one is dying low mass stars. So if all these elements or, all these things formed in these different regions in space, how come we have a sample of all that in Earth, in our planet? What do you think would have captured all these different elements and put it in our Earth? We have gold, we have silver, we have copper, iron.
So the idea is that, essentially, the idea is that stars are born in generations. First generation of stars immediately after the Big Bang contained only hydrogen and helium. They contained nothing else.
Right.
Once those stars evolved, they were able in their cores to process large number of heavy elements, all the way up through iron and nickel and a few heavier things. When those exploded, essentially that gas, that material was then put back out into the interstellar medium, into new gas clouds. So essentially you've polluted the gas cloud or formed that. Then the next generation of stars began to form out of these cooling gas clouds, and now you have polluted gas that's going to form the next generation of stars and planets. So we think that's how things were created on Earth. Our stars are not the first generation of stars. They're not the pristine stars left over from the Big Bang. We think our stars were probably formed our sun was probably formed 1 or 2 generations after that, and contains significant numbers of these pollutants, especially from generation and even second generation stars. This is actually a sort of newish field in astronomy. They call it galactic geology. What it is we're now starting to get large enough surveys of stars in our galaxy and beyond, where we can start to look at what stars in different parts of the galaxies have different chemical abundances, and start to figure out when super occurred and when they sort of polluted the gas of galaxies at a different rate.
Okay, so you mean to say all this happened due to some heavenly pollution that we got these things on Earth?
Yeah, pretty much. But to be fair, it's not that this occurred and then rained down onto Earth. It's that when Earth was formed, along with the sun, it was already forming out of this polluted gas.
Okay.
I guess maybe I should say enriched rather than polluted.
Okay. Do you think we can expect a similar spectrum of elements on other planets like Mars or Venus? Do you think it could be there?
That's a perfect understanding, is that because the entire solar system formed essentially at once out of a large collapsing gas cloud, essentially you expect the same chemical abundance on other planets. And we see that asteroids or meteors and asteroids.
Okay.
Or meteors again, at least.
Right. Thank you.
John, you want to ask your question? Let's see if I can unmute John manually.
Paul,
here.
John had typed in a couple earlier in the evening. Just scrolling back. One of them was a question about what is the rate of time around a neutron star compared to free space?
So that's, what happened, due to relativity, is that time in a gravitational field closer to the surface of the neutron star would appear to pass slower. Now, someone next to the neutron star didn't realize that, but someone observing that person would appear that they are moving slower. I don't know the exact number off the top of my head. Let's see. Yeah, I don't know the exact number off the top of my head. I'd have to work that out on a napkin.
Okay, and then he had another question near the beginning of the presentation when you were showing the first LIGO chirp. is asking, why wasn't the chirp shifted almost infinitely redward to black by the surface gravity of black holes?
Right. So this gets a little bit weird. And it is fundamentally confusing, right? Like the whole shtick of black holes, right, is that they, accrete everything and nothing can escape from them. How are gravitational waves escaping in the first place? The way to think about it, the way I think about it at least, is that the gravitational waves are not coming from the black hole itself. It's coming from the space-time around the black hole. And what happens is when those two things merge, created this new distorted space-time around the black hole. And the waves are actually parts of the things that have not into the event horizon yet, escaping outwards. Another way to think about it is that, so we talk about black hole, technically every mass emits gravitational waves. The Earth orbiting around the sun emits, every mass that is rotating, moving in some way in 3D space. So the Earth orbiting around the sun emits gravitational waves. If I was to stick my arms out and spin, I would technically emit gravitational waves. The thing is, space is extremely stiff, and so you need something very massive moving very quickly in order to actually deform space-time appreciably. This movie that I showed earlier is one of the few movies that I have that is actually slowed down how quickly it happened. These black holes at the end of their life were orbiting at about 50% the speed of light. So these are massive objects very close to each other, moving very, very quickly. And that's just barely enough to vibrate space-time enough for us to actually detect it here on Earth.
So that kind of puts it into perspective. Thank you.
Yeah, and that goes back to what I was saying. These are incredibly energetic events. Like the amount of energy in these things is just, it's beyond astronomical.
Okay, Paul, those are the questions I saw from John.
Yeah, I think I scanned through also. I don't see anything else. Does anyone else have further questions for Carl? George, go ahead.
Yes, in your origin of the elements, you have low mass stars producing really heavy elements. Like down here. Well, these elements, how does that happen since you really can't do fusion up beyond iron? You can't even, with low mass stars you have up here, mostly they form this carbon and nitrogen. So how do they make these even heavy elements like lead?
Yeah, so the dying low mass stars, what we think this happens in is the atmospheres of certain low mass stars. So asymptotic giant branch stars. We still don't entirely understand this, which is why I was a little shifty about that when I was talking about it at the end. Essentially, we think these pulsations may allow you to create these elements, but that part's actually still a little uncertain.
Some stars produce elements like the radioactive decay. They must be produced more or less recently, very heavy elements right in the stars. So how does that happen?
Well, I mean, I think the idea, right, is that most of the things we see on Earth in large quantities, like the quantity we see them in is proportional to A, how much was created initially, and B, what their radioactive lifetime is, right? So anything that it has a half-life is largely already decayed. And so I think, I mean, why these are considered trace elements, right? Like there are some that are pretty rare.
Okay. Bruce, you have a question?
Yes, thank you, Paul. Carl, what are the different branches of mathematics that you use in your modeling of the celestial events? In particular, I've heard that a branch of mathematics called group theory is used by a cosmologist to do this, that, and the other thing. And in particular, these algebraists use something called the monster group. So that's the question. What are the different branches of mathematics that you have to wrestle with?
So I don't do much in group theory. I think group theory is mostly the domain of particle physicists and to a lesser extent cosmologists when they're working on early universe cosmology that involves particle fields. I work mostly in, so for instance, when we're solving here the gravitational in-body problem, that's largely just differential equations. This is fundamental in binary differential equation. Otherwise, when we're dealing with gravitational waves, that involves a field called differential geometry, because that's the math that Einstein's theory of relativity is written in. Differential geometry, essentially, I take some sort of shape from topology, and I want to know how I put a mathematical map down, right? So think of the analogy with a map on Earth and the actual the Earth itself is a sphere, and we create these maps that try to represent the Earth in terms of longitude and latitude. These notes that we use. That's kind of what differential geometry is all about. You want to find sort of maps that you can use to describe the curve, and then, or the curvature really of any object, and then you try to express how the curvature relates to the motion of those objects using the Einstein field equation.
Carl, let me just ask a footnote question. Does non-Euclidean geometry ever figure into any part of your work?
Oh yeah, I mean the relativity is explicitly on Euclidean geometry. It's actually what's called pseudo-Riemannian geometry, and so because technically once I go to curved spacetime, even in Einstein's theory, even if there is no mass, I technically have, by unifying space and time, I've technically done a way that is non-Euclidean. And once I'm dealing with curvature like this, things are very non-Euclidean. So essentially when I was describing earlier how things curve in the same direction, that's all explicitly non-Euclidean.
All right, well, thank you.
Sure.
Any last questions from anyone? Carl, we deeply appreciate your sharing the time with us, and it's a great presentation, very insightful. If you're ever up in this
thank you all
area,
for having me.
Yeah, if you're ever up in this area, we'd be glad to see you at one of our meetings, okay, or come out and hang out with us.
Sounds